talk about one of the most classic examples of a series with non-negative terms. So this series is called the harmonic series, and the harmonic series is the sum from n equals 1 up to infinity of 1 over n. So the terms look like 1 plus a half plus a third plus a fourth plus a fifth, keep going. To consider this, what we can do is we can talk about it graphically. So we can look at it graphically in the sense that this has a width of, this bar here has a width of 1, and I've given it a height of 1. So this first bar is representing that plus 1. This second bar has a width of 1 and a height of a half, so it has an area of 1/2. My next bar has an area of a third, and my next bar has an area of a fourth, and so forth, so forth, so forth, so forth. So I can actually represent this thing graphically in a very nice way. And I can actually do this for any series with non-negative terms. But we want to know about the harmonic series. We want to know, does the harmonic series converge, or does the harmonic series diverge? Take a second, pause the video, and make a guess, or try and convince yourself one way or the other. Do you think the harmonic series converges or diverges? Okay, so to decide whether or not the harmonic series converges or diverges, we need to actually consider the partial sums, because remember that a series only converges when the sequence of partial sums, when the limit of the sequence of partial sums also converges. Like that is the definition of the series converging, is that the sequence of partial sums converged. All right, so let's look at our nth partial sum, s sub n, and it looks like 1 plus a half plus a third. Keep on going until you get an nth. Well, this is great. So we have our s sub n, and we can look at it graphically over here, but when I'm thinking about the area over here, classically what comes to mind is doing integrals, right? And what more useful thing to do here than to find a function that's going to match up really, really nicely. And I have one in particular in mind that's going to hit all of the things that we need. Hit down here. And the graph that we're going to look at is this one, and that is in fact the function 1 over x. And the reason that I need to think about this function is because if I'm thinking about area, I'd like to integrate. And if I'm going to integrate, well, then I need to have something that's continuous, so I have to have a function. So I've chosen myself a function that's useful, and now I can kind of consider integration. Now notice that if I integrate this function, well, up here isn't going to do me any good, which is part of why I want to start at 1, but also if I start integrating at 1, I'm actually going to overshoot how much my area, or I'm going to undershoot how much my area is. I'm actually losing area. So my partial sum is going to have more area than my integral is. Let's rewrite our partial sum in a more useful way to try and see how we can substitute in this area. So we're going to take our partial sum, and I'm going to reassociate it. I'm going to take the n minus 1th term, and I'm going to add that to the first, all the first n minus 1st terms together, and then I'm going to take that nth term and I'm going to let it be on its own. So I haven't changed anything. All I've done is reassociation. I've just moved this out by itself. And now, do you agree that this part right here that I've reassociated, that this is an area that's greater than the integral if I had gone from 1 all the way up to n? So just think about if I was looking at s sub 4, right, that would be all 4 of these. Well, I would only want to go from 1 to 4 to integrate, but I'd only catch the first 3 terms, and I need to add on that 4th term. So in fact, I can say, hey, s sub n is greater than or equal to that integral from 1 up to n of 1 over x dx But then again, I don't want to lose the last term, so plus that 1 over n. And now if we look at actually evaluating that integral, right, those are numbers. I've got 1 and n, so I can actually evaluate this. This is going to be, remember when you integrate 1 over x, you have the natural log. So this is actually going to be equal to the natural log of n minus the natural log of 1. And we all know that the natural log of 1, this is just 0, so this whole thing is really just the natural log of n. So let's rewrite our results down below. So what we have right now is we have s sub n is greater than or equal to the natural log of n, right, from here, because I don't need that natural log of 1, plus 1 over n. And remember when we started this, I said we're trying to decide if it converges or diverges, and we need to know if it converges or diverges by looking at the limit of the partial sums. So I want to know the limit, what happens as n goes to infinity of these partial sums. Well, if this is greater than that, then the limit of this should be greater than or equal to that. So the limit as n goes to infinity of the natural log of n plus 1 over n. I'll put that around it so that we know what happens to 1 over n as n goes to infinity. This is going to go off to 0. That's obvious. But what happens to the natural log? And if you think about it, remember the natural log increases and it doesn't stop increasing. It is an increasing function that goes to infinity. So this actually goes to infinity. So this is, in fact, positive infinity. The natural log increases. It just increases really, really slowly. So it looks like it's tapering off, but it's not. It's just taking it forever to get to infinity. And so, in fact, what I've shown then is that the sequence of partial sums is infinity. Its limit is infinity, and so this means that the series must diverge. So let's wrap this idea up for ourselves. So the sequence of partial sums diverged, which implies that the harmonic series diverges. So the harmonic series diverges because we've shown its sequence of partial sums diverges. And this is classically one of those series where your a sub n goes to 0, but the sequence of the terms goes to 0, but the series diverges. And remember, we have this idea in our head from the basic divergence test that if you can get your sequence of terms to go to 0, then you must converge. And that's just absolutely not true, and the harmonic series is the classic example that shows you why that's not true. So the harmonic series is in fact divergent, and this is one of the many proofs as to why it is.